Hi, welcome to the interrupts video for the Intel 8080, 8085 and Zilog Z80. This video is part 1, where we'll cover the shared interrupts of the 3 CPUs. For part 2, there will be a dedicated video for the 8085 and the Z80. So what is an interrupt? Let's have a look at a standard program flow. The main program is running, and you want to check your peripherals. Suppose this device is a keyboard, but it can be anything. It's just an abstract view. In your main program, you have to call the subroutine periodically to check if a key was pressed. This process is called polling. If there's nothing pressed, the main program can continue. If you do this polling too often, your main program may slow down dramatically. But if you do it less frequently, you may miss data or the information flow is lagging. So this time there's data available, and the CPU will jump to the device subroutine, process the fetched data. After that it will return to the main program. A better solution is to use a device or a circuit that can send an interrupt. When data is available, the device informs the CPU immediately. The CPU stops the main program and jumps to the particular interrupt routine and processes the data. After that, the CPU returns to the main program. How is the CPU informed? Let's have a look. On the left side, for the 8080, the interrupt signal goes to pin 14. For the 8085, it's pin 10, and for the Z80, it's pin 16. On the Z80, the interrupt is triggered when the signal goes from high to low, and for the other CPUs, when it goes from low to high. What do they share? These are maskable interrupts, which means they can be enabled or disabled by software. If the interrupt mode is enabled and the CPU acknowledges the interrupt coming from a device, that device will send an instruction on the data bus, which will be processed by the CPU. It is usually a reset instruction. We will see these reset instructions shortly. The 8085 also has a trap interrupt. It is a non-maskable interrupt, which cannot be disabled by software. The Z80 also has a non-maskable interrupt on pin 17. The 8085 also has 3 further maskable interrupts from RST75 to RST55, which I will cover in a dedicated video. The pins SOD and SID stand for serial out and serial in data. Yes, the 8085 has an integrated serial port, which I will cover in the next video. The Z80, on the other hand, can put the interrupt pin in 3 different modes, which I will cover in a dedicated video. Let's have a look at these ominous reset instructions, also called software interrupts. These are often used to call system functions in operating systems. The first one is called RST0. The machine code is 1 byte long. To make it clear, you can use this instruction in your code, or the interrupting device can put this command on the data bus, and the CPU will execute it. You can compare it to a call instruction, but it takes only 1 byte instead of the 3. In other words, the stack pointer will be decremented and the program counter will be put on the stack and set to the new destination address, in this case 0. With the return instruction you can jump back to the saved address. With RST1, the destination address is 8. In total, there are 8 reset instructions, all separated by 8 bytes. The interrupting device could also put a call instruction directly on the data bus, but then the CPU has to generate additional interrupt cycles to transfer the extra bytes. enough theory, let's start with the simulation. If you want to skip the Intel part, you can jump immediately to the Z80 example at 26 minutes 34 seconds. The Intel 88 or 8085 starts at address 0. That's why in your system your ROM or PROM must also begin at address 0. So, as we have seen with the reset instructions, they will call addresses between 0 and 38. It is a good practice to jump after the interrupt entry points. So let's jump to label init and put the init at address 40. That's just an example. Here I will load or set the stack pointer with the address FF, and you would do other initialization stuff. But for this example, I want to show you the reset command. The first one I will use is the reset 1 and the reset 7. A halt command, and here we have to specify the address entries for RST1. RST1 will jump to address 8. Let's put a return here, and RST7 will jump to address 0038 and also return here. So the RST commands are 1-byte commands. So the program count is 0. We're going to jump to address 40. 40, setting the stack pointer to address FFFF. Was already FFFF. And the first command is RST1, which will decrement the stack pointer and put a program counter on the stack and jumping to address 8. Decremented it once and put the program counter on the stack. 44, it's the address for the next command. Jump to address 8, executing the return, and he's returning back to 44. Next command is RST7. We will jump to address 38. 38 has put 45 on the stack and returning back. Normally you won't have a return here, but a jump to your interrupt function, because there's not enough space here for a program. The next interrupt entry point would be 10, and that are only 8 bytes. So you would have here a jump to your function. But in our case, or for our purpose here, it's enough. I will just do a load of the accumulator, and here also load of the accumulator, but with a different value. Removing our reset commands and writing a small loop here. That's an endless loop, just to pretend the program is running something. So we are in our endless loop, and our interrupts, the non-maskable interrupt trap is always enabled. But to enable the maskable interrupts, you have the command enable interrupts, and to disable them you could use disable interrupts. Enable interrupt is a 1-byte command. Enabling interrupt. So the maskable interrupts are also enabled. And we are again in our main loop. I hit the interrupt here. That will pop up a window here where you can choose the interrupt number. So I will choose 2 here for RST1. It will jump to address 8. So the device will put, in this case, the command RST1 on the data bus, and the CPU will execute it. So we'll jump to address 8, has put the return address on the stack. Loaded the accumulator with 8, and now we're turning back to the main loop. And here you can see the interrupt are still disabled. And this is a bug. The trap shouldn't be disabled. Even if you're entering an interrupt where the interrupts are automatically disabled, the trap, the hardware interrupt here, the non-maskable interrupt here, should always be enabled. That's a bug in the simulator. Okay, so for every interrupt routine, you have to enable the interrupt before you return. Here the same. Let's do it again. We're on the main loop, doing interrupt here. I choose 7 here. So the interrupts are disabled again, because we are in interrupt, but the trap shouldn't be disabled. This time it's the address 38. Accumulator is loaded with 38, enabling the interrupt again and returning to the main routine. The problem you will encounter here is that if you want to change your own interrupt routine, and this is programmed in the ROM or PROM, you can't change it. That's why you will have normally here a jump to a memory address, and then from the memory address you will jump back to either a ROM routine or your own routine. There are several ways to do it. I will show you 2 today. Let's start with the first one. Pushing HL on the stack. Loading HL with a value from the memory. Let's suppose it's in a memory address 7900. Doing an exchange with the stack and the HL register, and returning from the interrupt. So here I will specify the memory address, and here we will jump to the address, let's say 8100, and we have of course to specify 8100 here, where we'll put an operation and an enable interrupt and a return. So we are in our main loop. If you're doing an interrupt here, let's take the second one, RST1. It will jump to the address 8. So the return address is on the stack. It's 44. That's a loop. Has pushed HL also on the stack. Now we are loading to HL the 16-bit value from the address 7900. And 7900, it's the address 0081. High byte 81 and low byte 00. The next command, xthl, will exchange the values in HL with the values in the stack, which is pointing to address here FB. So we'll put the value of HL here and putting the value of the stack here. So the return address will be 8100. You have to remember it's always low byte, high byte. Return address is 8100. Operation, enabling and returning back to address 0044. 0044, we are in our main loop. We can do this also for the other interrupt. Doesn't want to be copied. I choose address 2 here. And address 2. Let's specify it here in bytes. This was a data word, that's a data byte. Let's take here it's low byte and high byte. And doing the same here. 8200. Operation, enable, return. Endless loop. This time I choose reset 7. So we will load from the memory address 7902. Returns to that address, return, and he's back in our main loop. So this method I have seen in the microprocessor 1, and the next method I want to show is a little bit more complicated, and I have seen it in the Minimax board. So let's call a method here. I will call it interrupt handler. specify a byte here, and I will choose the same value as the interrupt address. For the next one, I will do the same, calling the same interrupt routine, but specify here a different value, that's 38. And now we have to specify the interrupt handler. Let's put it here. Interrupt handler. And there I will do an exchange HL. And then saving the accumulator on the flex. Putting the value from memory to the accumulator, loading HL with a value from the memory address 7900, putting accumulator back to L, retrieving our accumulator and flex, and doing again an exchange and an return. So here I will erase it. 8100 is okay, but here I have to specify 8 and the other one is 38. So again here you would normally jump to another place in the memory, and here the same, but for this purpose it's okay. So we are again in our main loop, program is running, we're doing an interrupt here, sending the command rst1. We are now at address 8. Let's check the stack here. First he has put, the first return address is 0044, and the second return address is 00B0, 0B. The next command is do an exchange with the stack pointer and HL. So HL is saved here, and the value of the stack is 000B, and 000B is here. We are right here. So the next command is pushing the accumulator and the flex to the stack, and the next command is loading from the memory to the accumulator. Memory is specified with HL, that's 00B, the value is 8, you will put 8 in the accumulator. Loading from memory address 7900 the value, and that's 8100. So 8100 is loaded, putting to L the value from our accumulator, so the new address is 8108. I will just show the stack again, retrieving the accumulator and the flex, and doing exchange again with HL and the stack. So the HL registers are restored, and the new return address is 8108. So with return it will jump to 8108. 8108, the operation, enable instruction, and returning back to our main loop. So if you choose standing or reset 7 here on the bus, it will jump to address 38, calling the same subroutine. But this time it will jump to address 8138, because here's the value 38. (8138), and we're again in our main loop. In the next video I will explain the trap RST756555 and also the serial ports SID. Stay tuned for the Z80 example. Otherwise, see you in the next video. Thank you for watching. Bye bye. The Z80 starts at address 0. That's why in your system, your ROM must also begin at address 0. So, as we have seen with the reset instructions, they will call addresses between 0 and 38. It is a good practice to jump after the interrupt entry points. So let's jump to initialization procedure. I will specify here at address 006E. That's just an example. Call it init. And here you would do your initialization stuff, like setting stack pointer and so on. The first instruction I want to show is the reset instructions. And for example, let's take 08 and the next one 38. I won't do all the reset instructions. And a halt, and of course we have to specify the entry points here. 008, let's put in a return here, and 0038, also return here. So 1-byte command. So program counter is 0. It will jump to 6E, and 6E we're setting the stack pointer to FF was already FFF, and the first reset command, what will he do? He will decrement the stack pointer by 1, putting the program counter on the stack, and jumping to address 8. So decremented stack pointer and put the address 0072 on the stack. It's low byte, high byte, don't forget it. And 0072, it's the next command. So we are at address 8, there's a return, and we will jump back to 72 and do the next instruction. So this time 73 is on the stack. That's a halt command. Returning from the interrupt and doing the halt. So here in the interrupt routine you would normally jump to another place because there are only 8 bytes. You have only 8 bytes here. The next entry point would be at address 0010, and that's not enough for normally a program. So here you would normally jump to a different place, but for this purpose I will demonstrate it here. loading the accumulator with 8, and here loading the accumulator with 38. Here I will remove the reset instructions and writing a small loop. It's an endless loop. So it's running in the endless loop, and you can see here the interrupt is not enabled. So we have to enable the interrupt first. Let's do it here. You can enable the interrupt with the command enable interrupt and disable it with disable interrupt. Okay. Enable interrupt is also only a 1-byte command. Enable interrupt. You will see here interrupt is still disabled, and the interrupt control flags F1 and F2, I will cover that in the next video, are 0. So enable interrupt. Nothing has happened here, only after the next instructions it will enable interrupt. So now the flags are set to 1 and the interrupt is enabled. It's running in the endless loop. Hitting interrupt pops up the window, and here you can specify 8 different interrupts. Let's choose 8, that's number 2 here. So the device, the interrupting device, will send the instruction RST08 on the data bus that the CPU will execute. So here we are at address 72. The interrupting device sends now the command RST08, and the CPU will jump to the address 8. Interrupt, loaded the accumulator with 8, and returning from it. And you can see, I forgot to mention that during interrupt it disables further interrupts. Not the non-maskable interrupt, but the normal interrupts. So after every interrupt handling, like here, before we return, you have to enable the interrupt again. Same goes for here. Interrupt is enabled. Let's take this time 38. That's 8. It jumps to 38. Interrupt is now disabled. There can't be another interrupt. And loading the accumulator with 38, enabling interrupt, but it will only be enabled after the next command, which will be return here. And now the interrupt is enabled again. Last check. Again 8, and its accumulator is loaded with 8 again. Because this is programmed in your ROM, you couldn't modify it. If you want to change your interrupting routines, you would have to modify your ROM or PROM. That's why normally here you will have a jump to a memory address. From that memory address, jump back to a routine in your ROM. And there are several ways to do it. I will show you two. The first one, I think I've seen it in the microprocessor. It's a board I've already covered or already showed. I think it was Number Invaders or something like that. You would have the following commands here. You would do a push HL, then loading HL with a 16-bit value from a memory address. Let's suppose it's something under address 7900. And you would do an exchange with your stack pointer and HL, and here doing a return. So we can see here it's 1, 2, 3, 4, 5, 6 bytes. That's still under 8 bytes. That's okay. So let me specify here 7900. And here I will do an give him an address. Address where the routine is. Suppose it's under address 2000. That's 2000, low byte, high byte. And specify here 2000, putting here an operation, enable interrupt, and a return. Okay. Let's have a look here. So, running in the endless loop, doing an interrupt, 8, that's why I put 2 here. You jump to address 8. So what happened here? He has already pushed HL to the stack pointer. That's this one, that's FB. Stack pointer is at FB. The next command is loading HL with the value specified in 7900. So here 7900, there's the address 0020. So high number 20, high byte 20, low byte 0. Here with the commands, exchange stack point HL, I have already covered that in a previous video. He will swap HL, I will put HL on the stack, and the values from the stack will put it to HL. So it swaps them. So now the return address is here. Here, 0020 return. You jump to address 2000. Some operations here. Enabling interrupt and returning. Returning back to 0072. And that's in your loop. So if you want to modify your own interrupt routine, you would just modify in memory the entry points. For example, address 8500, and you would put your own routine on address 8500. If it's a different interrupt, you could have something like this. For example here, you would say at address 2, 7902, and here we would put, you can use double byte or as data byte or data word, and here, for example, say it's address 3000. Interrupt 38, that's 8. And he will jump to address 3000. Well, they're only in operations here because I haven't put code in here. Okay, let me show you another method I have seen on the minim export. That's very interesting. Okay, remove this. And here we are doing a call. Let's call it interrupt handler. And here I put a value, and the value I will use the interrupt value. Doing the same here. Calling the same interrupting handler, and here I specify .38 because it's interrupt 38. Here I specify our interrupt handler, and I will do an exchange stack pointer with HL, pushing the accumulator and the flag register on the stack, loading accumulator with the value of HL, and then loading HL with the value of the memory address 7900, putting accumulator to L, popping back the accumulator and the stack, accumulator and the flags, and doing an exchange again with the stack pointer and HL, and a return. So we can remove this, keep this, but I will put 8 here. So normally you would have also a jump here to a different place, but for this purpose it's enough. We are in our endless loop, doing interrupt 8. So we did a call to the address 76. Let's put the return address on the stack. Doing a swap with the stack pointer and HL. saving the accumulator and the flex to the stack pointer. That's the other two FFs here. And loading the accumulator with the value of HL. And HL is 000B. And 0B, there's a value 08. So we load that in the accumulator. Accumulator is loaded. Now he loads the value of the address 7900, which is 2000. Putting accumulator to L. So the new address is 2008. Popping back the accumulator. Doing exchange again of the memory with the stack pointer, or with the stack. So HL will be put here, and where are we? FFP here. And the value of the stack back to the HL. So we have the return address here. When we do a return, it will jump to address 2008. It's an operation, enable interrupt, and return. If you do now a jump to the address 38, it will jump to the same subroutine. But this time the accumulator is 38. So we'll jump back to the address 2038 with a return. 2038. So you're always calling the same interrupt routine here, but you're making the difference with this value. This value or this value. If it's another interrupt, you will put that interrupt number. And with this address, you're specifying the new address routines. In the next video, I'll recover the non-maskable interrupt and also the two remaining interrupt modes. This sample was running in interrupt mode 0. I hope you enjoyed the video and see you in the last part. Thank you for watching. Bye bye.